Hello students, this is Shakil and today I'm going to discuss a very important topic from AS Physics, that is deformation of solids. It is the last topic for general physics of the syllabus. So if we look upon the syllabus outlines, we have to look upon generally many things from O levels as well. Let's say we have to make ourselves familiar with load extension, compression, limit of proportionality in Hooke's law. Then we have to look for new terms, stress, strain, and Young modulus from AS syllabus. We have to describe an experiment to measure Young modulus of metal. Then elastic and plastic behavior of objects. We have to study about that. And then we have to deal something with the graphs. Okay, so let's move on to the first thing. The basic thing is deformation. So everyone knows that deformation is what? It is change in shape, size, or dimensions of an object due to a force acting on it. Well, one of the effects of force, along with many other, is that it deforms the object. So the force that deform an object is known as deforming force. Well, there are three types of deformation. The first one is in our syllabus, which is tensile deformation. Deformation means change in length, which can be extension or compression. So tensile means along length. So it is one-dimensional deformation, like only the length can be increased or decreased. If the length increases, it is extension. If the length decreases, it is compression. And this is change in length only, with that is touching or compressing. Two other types which are not in our syllabus, but we have to know them. One of them is shear deformation. It is 2D deformation. Let's say it is a change in area of the object after deforming force acts on it. The third one is volumetric deformation. That is 3D deformation, and it is the change in volume of the object. Well, we have to look upon elastic solid now. Elastic solid is an object that can recover its original dimensions or shape after removal of the deforming force. Like you apply deforming force, you changes the shape of the object, but when you remove the force, the object get back to original position. Okay, example is rubber band. Like in this case of the person, you can see that he is stretching the band and with his force that is exerted by the arms, and when he release it, the rubber band get back to the original position. In the similar way, you can look at when this weight is on the spring, it is in compressed form, but when you release it, the spring get back to its original position. So the spring is elastic object and the rubber band is also elastic object. What is load? Load is the force applied on elastic object that deform it, like the force the person is exerting on the rubber band, or this load which is placed on the spring is known as load. It is actually the name for the force. What is extension? Extension symbol is E, or it is delta L. Delta means change, L means length, change in length. So extension is the increase in length reduced in elastic object due to deforming force. So extension is basically increase, how much length increases. If you look in the diagram, the original length is still here, but when you put some load in that, so the length increases. So the increase in length of elastic object due to some force is known as extension. And now to find it, we use formula extension is new length minus original length, or it is like stretch length minus original length. Well, about compression, it's the same thing as extension, but it is decrease in length of elastic object due to a deforming force. Well, compression is actually original length minus compressed length. It's the other way around. So X is L naught minus LC. L naught is original length, LC is compressed length. And you have to note that change in length symbol can be used to represent extension or compression. So you can see in this diagram, originally the spring is unstretched, but when the force is being exerted on it, so it is being compressed now. What is limit of proportionality? It's a common sense thing. It is a point in the graph till where the two quantities are directly proportional to each other. Like you plot a graph between two quantities, and till the point till which the line is straight, it means like both the quantities are directly proportional. Well, the famous Hooke's law, you have done that in IGCSE as well. So what is Hooke's law? This law actually provides a relationship between applied force and deformation. Its statement is very common. The change in length, which can be extension or compression, in elastic object is directly proportional to applied force. And there is a condition for this law, provided that elastic limit has not been exceeded. Like you don't have to apply too much force so that the object exceeded its elastic limit and it cannot get back to original position or it is permanently deformed. So the change in length produced is directly proportional to applied force or applied force directly proportional to change in length. When you convert this proportionality into equality, you have to assign a constant sign over there. And that constant is actually K. So this is the equation for Hooke's law, F equal K delta L. And you know delta L is extension. If it is extension, it can be written as F equal KE. If it is compression, it can be written as KX, or it is generally written as K delta. So this is the expression. Okay, now this K in the expression is the elastic constant or spring constant, commonly known as spring constant. So this elastic constant is F over delta L. So we say that elastic constant is defined as force required per unit change in length of elastic object. Like how much force you require to produce unit extension or compression or unit change in length, that is known as elastic constant. Its unit is Newton per meter, and elastic constant value determines the stiffness of the object. Like if any object is having higher value of K, it means you need to apply greater force in order to change in its length. Okay, now let's say if K is 2.5 Newton per millimeter for a spring, what does that mean? That means that in order to stretch that spring by 1 millimeter, you have to apply a force of 2.5 Newton. Okay, next is the graph. We know that from Hooke's law, F and change in length are directly proportional to each other. So this graph, if you plot a graph between this force and change in length, it would be a straight line and passing through the origin. Okay, now this graph has several points like O, P, L, and X. So first, let's look upon OP region, which is the straight line region. So over here, as it is straight line, so Hooke's law is being obeyed, and P is actually the proportionality limit. So P is the point till which force and change in length are directly proportional and Hooke's law is being obeyed. What is OL? L is the point beyond like P. Object behaves as elastic in this region. It means that no permanent change in length to this region, and object shows elastic behavior in OL. So L is the elastic limit point. It means that if you uh, load the object, let's say, so that will reach till L, and till L, like this is the force and this is the extension. And if you start removing the force from L, like you would not cross L and you start removing the force, then the object will get back from the same position to the zero. It means that there would be no permanent change in length. So in OL, object is showing elastic behavior. Well, about LX, the last region, which is LX, this actually shows the danger zone, and it means that in this region, the elastic limit is exceeded, so object deforms permanently and object show plastic behavior. Plastic behavior means that now object is permanently deformed and it cannot get back to its original position. But if you start removing the force from point X, then the object will get back to this new position. So this shows that object is permanently deformed because you have not applied any force at this point, but there is some value of the length. That means that object is permanently deformed. Okay, the next thing is the graph calculation. If you plot a graph of force against change in length, force if we consider the straight line graph, so the gradient gives us value of K, because gradient is y over x, y is f, and x is change in length, so f over change in length is K. It means that the gradient of force extension graph gives us elastic constant And for area under this graph, like you consider the complete area under this graph, like this graph, area, as you know, that area of any graph is product of y-axis and x-axis. This is just to find that which quantity you can determine from area under the graph. So it's like y-axis is f and x-axis is delta L. So f into L or f into D is actually work done. So we say that area under FL graph, F extension graph, gives you work done to deform the object or elastic potential energy stored in the object. Now let's look upon some string calculations. In this, you have to find change in length or extension or compression or spring constant or the load. Calculations will be there. There are several cases. Let's look upon them one by one. The first case is single spring case. So let's say if there is a single spring of length L naught, if you attach a load W and the new length is LS, so the extension is LS minus L naught. And of course, the spring constant is F over delta L or W over E, because in this case, let's say the extension is E. The extension is E and K equals W over E. Now let's solve an example. If let's say a load of 10 Newton produces extension of 1 centimeter in spring A, and then there is a spring B as well. In spring B is having twice the spring constant as that of A. Find the extension in spring B if 15 Newton of load is hanged. So it means that you have to do something. Well, let's do with spring A. So spring A elastic constant or spring constant is F over E. F is like 10 and E is 1. So it is 10 Newton per centimeter. Now for B, the spring constant is twice. So it means that spring constant for B is twice of spring constant of A. So it is actually now 20 Newton per centimeter. And now how much extension is there? So we say that, okay, F equals KE and E equals F over K. So the force is 15 Newton and the value of K is 20. So when you divide it, you'll get an answer of 0.75 Newton per centimeter. So it means that you require lesser amount. Well, it is actually centimeters. So you so the extension is 0.75 centimeter in this case. Okay, let's move forward to case 2, which is series spring combination. So let's say this is the arrangement in which the single spring was there, having spring constant K, extension E. And now the same type of springs, the two springs are connected in series, end-to-end series. Their original unstretched length is 2L naught. And when you extend the same load W as you have inserted with the single spring, you have to find new stretch length or the total length. You have to find the total extension and you have to find the spring constant for their series combination. So for total extension, we have to see that this weight W is actually exerting on this spring as well and being exerted on this as well. So as we can see that the single spring produces extension, like in single spring, the weight W produces extension E. So it means that in the top spring, extension is E, in the bottom spring, extension is E. Why? Because the same weight is being exerted on both the springs. So that's why the extension would be same. So in order to find the total extension, what we'll do is we'll add the extensions of single of the two springs, right? So in series combination, you always add the extension of two springs to find the total extension. And for total length, it's quite obvious. 2 times of original length equal plus total extension. So that's how you'll get the total length. For the spring constant, well, for the spring constant, we have two formulas. One is product K1 into K2 over K1 plus K2, or the second method is the Hooke's law method. K is F over E, F is like the weight hung, which is W, and extension is the total extension of this system. So you can use either of them to find the total, like the spring constant of this combination. Okay, you have to note one thing, that if you have use the same load with the springs, like the single and the series combination, you use the same load. So then K is inversely proportional to E. So it means that you can use ratio method to find the value of K for the series combination, for which we have done the work in the previous slide. Like we can say that for the single spring, its constant, elastic constant was K and its extension was E. So for a combination of like series springs, two or more, we have to find its spring constant and its extension is ES. So as K and E are inversely proportional, so we are linearly multiplying them. Like K into E equals X into ES. That is like when inverse proportionality is there, we use in ratio method, we linearly multiply them. So from here, you can find the value of X, and X is actually the elastic constant of the spring in series combination. Okay, so now case 3, which is the parallel combination of the springs. This time you're going to deploy both the springs in parallel. Let's say this is the single spring system with extension E and spring constant K, and you mounted the two springs parallel to each other, and there is some rod beneath it. Okay, the original length is L0. So you inserted the same load with them. So this load actually pulls the spring to a new length of the LS. So now, as two springs are there, so this is our common observation that there would be less extension. Why? Because the load is going to be equally divided among both the springs. Like you inserted W, you loaded W weight with both of them, but W by 2 is acting on one and W by 2 is acting on second. So as we know that W proportional to E, so if you half the load, the extension would be half as well. So it means that the extension produced in the spring would be half, right? So now, if you want to find the total extension, there's a formula as well. Extension of the system equals single spring extension divided by number of springs. Like the extension in the single spring was E, and the number of springs here in the parallel combination are 2. So you can divide them to get the extension of the spring, or the method that I told you, like the weight equally divides among the two, so the extension also divides. So you can use that as well. For elastic constant, you always add the values of the K. So like you add K1 and K2 to get the total extension of the combination of the system. So in parallel combination, we know that the extension will decrease and K and E are inversely proportional, so the K will increase. So when K will increase, it means that it is harder to stretch these springs. Now let's look upon case 4, which is like series and parallel mixed spring case. Like let's say we are using the same spring, identical springs. The 3 of them are connected in parallel, then these 2 are in parallel, but these 2 are in like series, and then another one in series with them. So we have mixed combination of series and parallel. So when the load W is hung with a single spring, it produces extension E, and the elastic constant was K. It means they're saying that if there is a single spring and you hung a load W, so the elastic constant is K and extension is E. So if you hung the same load W with this combination, what should be the total extension and what should be the spring constant? Well, for the extension, we know that for W, it is E. So for this string, the weight is W, so extension is E. For these strings, as there are 2 strings, so weight is being divided equally, so there's the extension. And for this combination, the weight is divided by 3, 4, because there are 3 springs. So it means that extension will be divided by 3 as well in each of the springs. So as they are in series, so we know that in series you add the extensions as we have seen previously. So you have to add them. So the extension in the top one is E by 3. An extension in the middle one is E by 2, and extension in the bottom one is E. So you add them together to get the answer. So your answer, like the LCM is 6. So it is 2E plus 3E plus 6e. So it is 11 by 6e, which is the total extension. So 11e by 6. And for the spring constant, you know that spring constant at E are inversely proportional. So it would be 16 by 11k because they are inversely proportional to each other. Okay, now let's move on to one more thing, important thing, which is like the stress. This is a new term, stress, and its symbol is sigma. So what is stress? Stress is also related to deformation. It is actually having a same definition as that of pressure. So it is force acting per unit cross-sectional area of the object. So stress is force divided by area. So it's like similar to pressure. Sigma is F over A. Its unit is Newton per meter square, but we would not say Pascal because we don't have to confuse ourselves that pressure and stress are same thing. Actually, they're different. So let's see an example. There is a rod having like different thickness. So at the end, the area is 0.02, and in the middle, it is thinner. So it is the area having area of 0.01. So under Newton force is exerting on it, and it is pulling it apart. So you have to find the stress at the end point and at the midpoint of the wire. So we know that stress is force over area. So at the end point, force is 100 and its area is 0.02. So that's how you can get the stress, which will be 5,000 Newton per meter square. For the midpoint, the stress is force over area and the force is 100 and the area is 0.01. So it will be 10,000 Newton per meter square. So it means that from the relation, we know that stress is directly proportional to force and it is inversely proportional to area. So as it is thinner at the center, so more stress is applicable over there and the rod is going to break from this point. Now we have to look for a strain. Strain is the ratio of change in length to original length of the object, or the fractional change in length of object is known as strain, and strain equals change in length over original length. So change in length can be written as extension, which is E, and original length can be written as L. So it has got no SI unit because it is actually a ratio between two similar quantities. Well, there is a term related to stress and strain, which is Young modulus or modulus of elasticity. This term is similar to term density. This term is similar to the term resistivity. So Young modulus is actually material of the feature. It is actually like feature of material of the wire. So we can say that it is feature of material, just like density. Like for density, you can have any mass or any volume, but its density is same. So similarly, Young modulus of any material is same. It is not dependent upon any dimensions of the object. It just depends upon material. As far as material is same, Young modulus should be same. So how do we define it? It is ratio of applied stress to strain produced in an object. That's quite simple. Like it is stress divided by strain. Okay, so what are some of the features? Its symbol is E, and it determines the strength of the object, and all the metals have Young modulus in our reaction is 11 Pascal. Like every material is having its own value of Young modulus. So for its equation, we know that stress and strain are directly proportional. Like if you apply greater stress, greater strain will be produced. This is similar to force and extension type thing. So stress equal to constant into strain, and then you this constant is actually Young modulus, which symbol is E. So E is stress over strain. Okay, so the unit for E is Newton per meter square Pascal, and same as stress or pressure because strain is not having any unit. Okay, now we have to look upon its equation and also between a relation between Young modulus and elastic constant. We know that Young modulus is stress over strain. This is important. And stress is F over A, force over area, and strain is change in length over length. So force over area multiplied by length over change in length. And then finally you got this expression that strain Young modulus equal force into length divided by area into delta. From here, delta L, you make delta L as the subject, which is actually the extension produced as FL over EE. So like you can make the factors that for an elastic object, extension produced is directly proportional to force if you keep all other factors constant like length, area, and type of material. Like if you apply greater force, greater extension will be there. The second factor is extension proportional to length. Like for longer wires, more extension will be there as compared to shorter wires. And for the cross-sectional area, it is inversely proportional. Like thinner wires will be stretched more as compared to thicker wires. And then again, for Young modulus, it is inversely proportional. So if a material is having less value of Young modulus, you can stretch it more. Okay, now one more thing from this expression, this F over delta L, this F over delta L is equal to K. So in the expression, you can replace F over delta L with K. So this is your new expression, Young modulus equals K, which is the elastic constant, into L, which is original length of the unstretched material, divided by A, which is the cross-sectional area. So since cross-sectional area and length are always constant, so that's why we can say that Young modulus is directly proportional to elastic constant. Okay, now let's look upon the graphical analysis of stress strain graph. Like stress is plotted along y-axis, strain along x-axis. So the graph is a straight line because it's the Young modulus thing. Since you know that stress and strain are directly proportional, so the graph would be a straight line passing to the origin. And with all type of graphs, we have two types of calculations. One is the gradient, and the second one is area under the graph. So gradient here gives you the Young modulus. So the gradient of stress strain graph gives you the value of Young modulus because the y-axis is stress and x-axis is strain, and gradient is stress over strain, which is Young modulus. Okay, the area under graph is like y-axis into x-axis. Y-axis is stress, x-axis is strain. So stress is F over A, strain is delta L into L. So force into delta L is actually the work done to deform the object or elastic potential energy stored in the object. And area into length is actually volume of object. So we can say that the area under stress strain graph gives you work done per unit volume of the object or elastic potential energy per unit volume of the object. Okay, well, at the end, we have to look for an experiment to measure Young modulus of metal in the form of a wire. Well, this is an important topic from the deformation. It is related to experimental investigation type, like you have to describe an experiment that how you can measure the Young modulus of a material, and that material would be in the form of a wire. So we have to look for the experimental setup. There can be two types of experimental setup to measure the Young modulus. One is a serial apparatus and second one is simple tabular apparatus. So over here, we have to look upon both the methods. In order to answer our question, we can use any one of the material. So this is a serial apparatus and this is a simple table method. We will prefer simple table method. But what's the serial apparatus? Well, for the wire for which you have to measure the Young modulus, you connect that wire over here with a fixed load and you apply a reference scale or the vernier caliper scale. Then you connect the same wire, and then there is a mass hanger so that you can change the weight on it, and you will keep adding the weight on it, and it will be stretching down, and then this vernier scale is used to measure the extension. So in this combination, this wire is fixed, you will not change its load, and this will be the extension will be produced in this wire because you're going to add load over there. And this is the vernier scale, which will give you the extension in millimeters. Okay, about the second apparatus, that is quite simple. You will take the wire for which you have to measure the Young modulus. You will clamp it in the wooden block so that it would not move, and then you will pass it over a pulley, and then you will add some load with it. And then you place a millimeter rule over there, and then you have to use a marker on it, like this marker. It can be a piece of paper. So what you'll do is you will add more weight over here, and the wire will be stretching and the marker will be moving forward, and from here you can measure the extension. Okay, so now for we have to use the table method. So we know that if we want to measure Young modulus, its formula is FL over AE, force into length over area into extension. So firstly, we will have to measure the original unstretched length of the wire between the fixed end and the load. And then we have to measure the diameter of the wire using micrometer screw gauge. We will measure three diameter reading from three different points in order to overcome the random error in our reading. Then we take the average, and then we use the formula pi d squared by 4 to measure the cross-sectional area of the wire. Okay, then we will hang the different loads and find the extension produced by each load. And when we'll have some 5 or 6 sets of readings, we'll plot a force extension graph to find the gradient. And you know that gradient of FE graph is actually K. So it means from this expression, again, we can say that this force over E is actually equal to K, which is the gradient of FE graph. So we finally say that the Young modulus is equal to gradient of FE graph into original length over cross-sectional area. So that's how you can measure the value of Young modulus accurately. So if this question comes, you have to describe the whole process, like this experimental setup, this tabular method, and then all these steps. Okay. Lastly, we have to look upon deformation and its types. So deformation is having two different types, elastic deformation and plastic deformation. Elastic deformation is the deformation in um, objects till elastic limit point. Object can regain their original dimensions after removal of the force. Like elastic deformation is a temporary deformation. It is there till the time by which the force is there. If you remove the force, elastic deformation is gone. And you can look at it in the graph as well. Like if this is a stress strain graph, so you can say that this is the plastic region. Plastic region is still the straight line. Like till this point, if you remove the force, the object can get back to its original dimensions. For the plastic deformation, like P for plastic, P for permanent. So this deformation is produced after the object exceeds the elastic limit and the object cannot regain its original dimension. It means the object is permanently deformed. So in this region, object is having permanently deformation. Okay, well, this is again an important thing, area under FE graph. We know that area under FE graph gives us work done to deform objects, or it can be elastic potential energy stored in objects. But there are different regions, like the first area is OA, BT. So first we have to see that what this area represents, what type of energy this area represents. OABT, like OABD is this complete area under the graph. So this area actually represents work done to deform object. Like you have to do total work in order to deform the object. Okay, well, there is a second area, which is BCD, like this greenish one, BCD. Okay. This area, actually, if you look on the curve now, so this curve is known as loading curve. Loading curve means that you are applying force on the object and the extension is being increased. Then from B to C, it is unloading curve. Unloading curve. Unloading means that you are going to decrease the force, remove the force. So that's why the extension is being decreased. So area under BCD actually gives you useful work done. Like this is the work done that we are looking for. Like if you pull the catapult, so the input, you do some input work on it in order to pull it, and when you release it, the output work that you can get, or the output energy that you can get, is kinetic energy. So this area BCD actually represents the useful work done. Then there is a third area as well, which is like, I have to shade it with different color. um, Okay, let's say let's color it like this. So if you look upon this area now, which is O, A, B, C, this area gives you wasted work done, or this is actually internal energy stored in object. Internal energy in object. Like this is non-recoverable. This is non-recoverable. Like this is sort of wasted. This is sort of wasted energy. Because whenever you pull the catapult and release it, pull and release it, so of course some heat energy will be produced over there. So that heat energy will be represented by this area of O, A, B, and C. Okay, lastly, we have to look for some energy. So elastic potential energy is the energy stored in the form object, and it's equivalent to half Fe, where F is Ke. So when you replace F with Ke, so you get another expression which is half Ke squared. So that is known as elastic potential energy. So thank you, students. I hope that this video lecture was useful for you. What you have to do is you have to make notes from it, and we will be looking upon solving the challenging questions in the next video. So challenging questions is over now. Goodbye, students.